Good morning, everyone. I hope you're doing well today. Hello, Vishnu. Hello, Bongamusu. Hello, Dixon. Hello, Aswag. Hope everyone is doing well today. Dixon is representing from Zambia. Hello, NS. Hello, Ying. Hello, Kritika. Hello, Victor from Nigeria. Hello, Fahim from Afghanistan. Hello, Alejandro. Hello, other Victor from two Victors from Nigeria. Hello, hello, Malprince. Hello, Raul. Hello, Fernanda. Hello, Towo from Nigeria. Nigeria being represented well today here. Hello, Abdullah. What questions can I answer for you all today? Hello, James. I'm doing all right. Thank you for asking. I'm a bit tired, but such is life. Hello, so Abdullah from Sierra Leone. Hello, Martha. Hello, Muhammad. Hello, Andrew. What questions can I answer for you today? We could finish up this fast is prime function. How to work on algorithms. I guess what do you mean exactly? There are, let's see here. Can we discuss the last exercise in pi algorithms? Yeah, maybe we'll finish up this is prime function right here. We got most of the way done yesterday, and then we could talk about the last exercise in the pi algorithms notebook. What is the function of algorithms in data science? Maybe I'm not entirely certain what you mean, but I mean, right, algorithms are just general recipes for doing things. We always want efficient algorithms for doing things. Let's finish talking about this exercise 4, right? We started this yesterday. I mean, this right here, if you like, I mean, if you want to get technical about it, primality checking is itself can be viewed as an algorithmic procedure. I mean, any procedure you're doing in some sense is an algorithm, right? If I need to sort a collection of numbers, that is an algorithm. Sorting is something that we often have to do, and so we would want an efficient sorting algorithm. Python provides a sort algorithm for a list, so we don't have to program one ourselves, but we could do so if we wanted to do so. Right? Algorithms are largely about, well, I want to do something and I want to do that thing correctly. But there's a secondary concern is that, you know, I want to do something fast. Of course, correct is, the most important part of any sort of algorithm. Can I do what I want to do? Can I do it correctly? But we can't overlook the speed or the computation time or the complexity of the algorithm, however you want to phrase this. So as I said, let's finish talking about this is prime thing. Well, right, yesterday I wrote this function. Let me put a line spacing here just to emphasize. We imported the math module, and we had this is prime fast function. I copied and pasted the is prime function, but then I modified it. The first few cases, right, if this number is negative or 0 or 1, we return false. Check if the number is 2, then 2 is a prime number and return true. Otherwise, check if the number is an even number, and it'll be an even number larger than 2 because we've already taken care of the case when our number's 2. If it's an even number, well, then again, by the way we've written this function, this even number is larger than 2, and so therefore that even number is not a prime number. Otherwise, we know that this number now is an odd number. And then we can check for, odd factors. And as we mentioned yesterday, we only need to check up to the square root of the number. And we could therefore check in steps of 2. So this will check 3, and then 5, and 7, and 9, and so on. And then we check, is our number evenly divisible by this factor we're testing? If it is, we return false. Otherwise, we will return true. We have a prime number, right? And this, will give us a much faster algorithm for checking if something is a prime number. NKIT, when will we be doing the VC mini project? Well, when we're done with the IP mini project, we can move on to the VC mini project. So perhaps tomorrow or Thursday, we'll get started on the VC mini project. Right, so as I said, to use these words that everyone's been using, this right here is an algorithm. This is a primality testing algorithm. Primality testing isn't something that we often do in data analysis or data science, but this is an example of writing a much faster algorithm than the is prime function. So NKIT, as I said, probably either tomorrow or Thursday, we can get started on the VC mini project in the office hours here. Right, if we think about the running time, so we had this is prime function up above. Right, this is prime function if I'm checking to see if a number is prime or not. I more or less have to check almost a number of factors equal to the size of the number itself. So if I have a number, we'll call it n, I have to check nearly n different factors. In my is prime fast, if I have a number n that I'm checking, all right, I have to do a couple of quick checks here, but in this range function, well, I'm checking what? I only have to check about the square root of n numbers. And strictly speaking, it's about the square root of n divided by 2 numbers because I'm going in steps of size 2. Right, so n versus the square root of n, or the square root of n over 2, right? The square root of n over 2 is much, much smaller than n. So this algorithm right here is much faster. And we demonstrated yesterday, I mean, I reran this code this morning, and so of course I'm getting different numbers in terms of the actual execution time. But, you know, the main speed up in terms of the factor is still evident, right? This is saying my original is prime function here, and this run this morning was taking about 6 1/4 seconds to run on average. This is prime fast is taking, 338 microseconds. That's 10 to the power minus 6. So I have a much, much faster algorithm. I have a much faster procedure for this primality testing right here. What does this mean? Well, I could check a larger number for primality test. You know, if I give a fixed amount of time, I could check much larger numbers. And so, you know, having a faster algorithm, well, basically means I could do more work in the same amount of time. Doing more work in the same amount of time right here means I could check much larger numbers to see if they're prime numbers in the same amount of time. Right, again, it's doing n kinds of operations, you know, where n is the size of my number versus doing square root of n size of operations. And that's just significantly smaller. Yeah, I could talk about how I learned algorithms and how I practiced and so forth. So, right, there's, now return a function which will find all prime numbers up to and including n. So right now I just want to call this is prime fast function. I could do this with a list comprehension. Or, well, first let's write it as a, so primes is an empty list for number in range of 2. I don't have to start from 1. I know that 1 is not a prime number. Remember, return a function which will find all prime numbers up to and including n. So this is why I'm going, my range is going to n plus 1. Remember, because the final number is not included. So if is prime fast number primes dot append number, and then I could return primes. Right, start with an empty list. iterate over the numbers that I want to test. Oops, and yes, no, that's right. Right, start with primes, iterate over the numbers, the range that I want to check. If this is a prime number, well, append it to my list of primes. Oops, and thank you. And when I'm done, I will return my list of primes. Get primes fast of 101. Right, all the prime numbers starting from 2 up to and including 101, which is a prime number. Or get primes fast of 27. Well, I get all the prime numbers less than or equal to 27. And of course, 27 is not a prime number, so it doesn't appear in this list. I could do this in an equivalent fashion. Let me just copy the definition. Right, I could do this, create an empty list, do a for loop, do an append. I could do this in effectively one line of code with a list comprehension. I could say number for number in range 2 to n plus 1 if is prime fast number. Right, this list comprehension right here will give me the same result as these 4 lines of code here. And if you continue, writing Python code, well, what you want to learn how to write is list comprehensions like this. Why? Because, well, list comprehensions are commonly used in Python. So, right, you want to be able to read other people's list comprehensions. And in fact, list comprehensions run a bit faster than this kind of code, this equivalent code. Why? This is because the Python developers have spent time, optimizing lots of, code for list comprehensions. So yeah, Raul, the only deadline for many projects is the deadline of December the 3rd. Right, this is for all mini projects. That's the only deadline that you have. There's no deadlines for individual mini projects, just all of them by the end of the day of the 3rd of December. Right, so again, this function right here is equivalent to this function here, right? They'll give me the same results. The list comprehension is obviously a bit shorter code to write. There's less to write. And the get prime, this method with a list comprehension should run a bit quicker than this other method. Right? They're both correct. They'll give you the same answer. The list comprehension should run a bit faster than this other method. Right. And again, I could use the isPrime function right here, right? But of course, I have this faster method for checking primality testing, so I might as well use it here. So I could submit this get primes fast, and this will check. This will, there's some number, so there's some value of n that is being used. I can't remember what that value is, but it's said here it's yeah, I can't, we don't say here. We don't tell you what the number is that we're checking. So algorithms, there's a well-known book on algorithms. I don't know if there's an online version. This seems to be a online version here. Let me share this. So you can see here, right, this is Introduction to Algorithms by Corman, Leeserson, Vest, and Stein. Spell Stein. This is a rather well-known book on algorithms. It's used in a lot of universities for, an introductory course to algorithms. You probably can't see because it's too small. There's 1,313 pages in this book. Now, I certainly haven't read this entire book. I don't know everything in this book, but it's, you can see it's pretty comprehensive. It is kind of highly mathematical in nature. Let's see if I could, oops, that's not the window that I want to expand. But this seems to be available online for free. So you should be able to, you could download this. Again, they talk about role of algorithms in computing, getting started. You analyze a sorting method. Hey, that's a common way of starting to talk about algorithms. A standard bubble sort algorithm, the one that you probably first think of, right? I want to basically kind of find the largest element and, stick it at the end. And then I want to find the next largest element and stick that, right at the, or vice versa, right? Find the smallest element, put it at the beginning. Find the next smallest element, put it at the second location, etc., etc. That's slow. How I learned algorithms was, lots of reading and practice and trying things out. There's lots of talk about sorting because, it's a fundamental problem, right? A lot of algorithms begin sort your data, right? Step one, sort your data. So you want a efficient sorting method. And yeah, there's algorithms, Learning about algorithms involves learning something about data structures. How do we store data in an efficient way so that we can access this data, in a fast way as well? So, I mean, this is a good book. It's rather weighty in terms of the length. How to avoid mistakes? Well, first of all, at the very beginning, you're not going to avoid mistakes, right? This is how you learn things. You make mistakes, and then you figure out what's going wrong with your algorithms, and then you fix those mistakes. There's some discussion here about so-called the asymptotic notation, how we describe the running time of an algorithm. And again, this will be somewhat mathematical in nature. Page 43, it says. The order of growth defined in chapter 2. All right. I've not looked at this book in a while, so I don't remember, and they've come out with a new edition and so on. Right, but it's basically, it's essentially starting out like reading some sort of book like this and trying things out. Right, so this second chapter, right, again, there's, chapter 1, let's go back here. Chapter 1, as they even say here, before there were computers, there were algorithms. An algorithm is just a procedure for doing something. You could view a recipe, right, a recipe for how to bake bread or bake a cake or make your favorite dinner, right? That's an algorithm. Step 1, do this. Step 2, do that. Step 3, do this. Step 4, do this. Step 5, you're done. Here's your cake. Ta-da! A recipe is an algorithm. It's a procedure for doing some task. And big preface to the book. All right, chapter 1 provides an overview of algorithms replacing modern computing systems. They said, what is, an algorithm is any well-defined computational procedure that takes some value or set of values as input and produces some value or set of values as output. So it's a sequence of computational steps that transform the inputs to the output, right? And this is what we do anytime we're writing a program. Right, a program is basically, it's an algorithm that's implemented in a particular programming language. And so, as I said, right, a fundamental problem is sorting a list of numbers or strings, something that we can compare. if we're given this input right here, well, we want to produce this output. The sorted list of numbers. And how do we do this kind of thing? Well, there are many ways, even for a seemingly simple sounding problem. There's, I don't know, 6 or 8, different sorting algorithms that I could think of. Maybe not 6 or 8, but there's a bubble sort, there's a merge sort, there's an insertion sort, there's a quick sort. I'm up to 4 already. There's a shell sort algorithm. The method that Python uses to sort is called timsort. Tim being the first name of the fellow who came up with it. I'm up to 6. I think I mentioned search right, but here's these 6 different algorithms whose names I mentioned for sorting a list of numbers. How do these methods work? Well, they work in different fashions. Sorry, let me mute my Slack. Right, how do you do this problem? What's the running time of the algorithm? So, it's precisely what I'm saying. Many programs use sorting as an intermediate step. Sorting is a fundamental operation in computer science. So yeah, as Susan says, there's different running times, possibly, for these sort algorithms, the so-called big O notation. The fundamental first question about an algorithm is if the algorithm is correct. Interestingly, as they point out right here, an incorrect algorithm might not halt on some input sequences, right? We might have an algorithm that may not even terminate, or an incorrect algorithm might halt, but with an incorrect answer. They point out this interesting thing. Contrary to what you might expect, incorrect algorithms can sometimes be useful if we can control the error rate. So typically we want algorithms to be correct, but even if we have an algorithm which may not always give us the correct answer, there are some cases where that algorithm might still be useful. And so, yeah, right, this, good introduction to algorithms. What are different kinds of algorithms are available? What are, some applications? For efficient algorithms, we often need to use different kinds of data structures. Right, and we have data structures in the Python programming language, namely things like the Python list, a Python dictionary, a Python set. There are different kinds of data structures which are available. There's things like heaps and binary trees, or k-array trees in general. Right, but this book, as I said, it's probably going to be a bit rough going to read. but that's probably going to be the case for any book on algorithms. There's some initial hurdle of reading and understanding. How do algorithms work in data science? Well, if I'm doing some sort of machine learning task, right, that's an algorithmic procedure. I want to take some inputs and compute some outputs. Um, the later mini projects that we talked about, the data manipulation, the data analysis mini projects, there again, they rely on searching through data to find matches. Well, that's an algorithmic procedure, right? I want to find which I have to do some kind of string matching, right? The later many projects are looking at data from the National Health Service in Britain about different doctors' offices and drug prescriptions and so on. Where can we find more exercises to practice writing in Python? That's a good question. Let me make a note to myself here to see if I could locate some good online exercises. I can think of some references, but those are for more specific problems. I mean, in particular, dynamic programming, I could think of some references for, but that's a little bit more advanced, I think, to begin with. So, I mean, yeah, you could use websites like LeetCode and HackerRank. So LeetCode. LeetCode is a website you go for, right? It says here, enhance your skills, expand your knowledge, prepare for technical interviews. You have to create an account. I don't have an account on LeetCode. I do have an account on HackerRank. You could have things like basic problem solving, and I have a certificate already. Oh, all right. I didn't remember this, right? But you could say, I have there's the problem solving. This is more of the algorithmic kinds of problems. So problem solving, etc. These are more, algorithmic problems in nature. You have some particular problem that you want to implement, and they describe the problem. So let's look at one. You could work in different languages, Python, C, C++, etc. Right, but they give you some sort of problem. Array type data structure stores elements. You want to reverse an array of integers. Right, so you're given an array of integers. You want to you want to reverse the array of integers, right? And kind of you want to avoid using, in this case, I mean, you could do it, but it's not going to be helpful, right? You want to avoid using, you know, say Python's built-in method to reverse a list. So yeah, so websites like LeetCode and HackerRank can give you ways of you know, these exercises, right, for writing code, practicing your code. I don't know about LeetCode. On HackerRank. On HackerRank, right, like you have various test cases. And there you have a time limit. If your code doesn't complete in the time limits, well, then it will tell you. So yeah, those are the, you know, those are, I guess, a few of the websites. Yeah, thanks for the reminder, Susan. Yeah, so LeetCode and HackerRank are a couple websites that you could go to practice your, you know, your code. You have things like, I mean, there's Python language exercises. There's problem-solving exercises, which, you know, are designed to be more algorithmic in nature. And of course, you could implement the problem-solving kinds of exercises in whatever programming language that you want to use. But of course, if you're trying to learn Python, it will be useful to, you know, program in Python, even if you know some other programming language. Right, but you know, any of these problems that we've already written code for right here, you know, these are algorithmic in nature. Some of them are very easy, right? You know, I don't have to write an algorithm to compute, you know, 2 raised to the power p. This is something that the Python programming language does for me, right? But you know, definitely this is prime function. This is an algorithm. You know, this is a way of taking an input, in this case a number, and returning some output, which in this case is a true or false. Again, the get primes right here, this is an algorithm. I take 2 inputs and we're returning this Python list. So everything that we have written right here, you know, we can view all these things as algorithms. They are taking some input and giving us some output. Let's talk about this last exercise in the IP mini project. So you know, we're going to, as it says here, we want to develop an even faster method, which is known as the sieve of Eratosthenes. I think Eratosthenes was Greek. I'm probably saying his name incorrectly. Apologies if you're from Greece. I'm butchering his name. So this method Oh, sorry. Yeah, can you check the last exercise in the algorithms? Apologies, I did forget about that here. So, PY algorithms. Where's the last exercise? Do you mean this insertion on a list? Is this a question that you mean? So, binary search. So, do you understand binary search? Have you written a binary search procedure? I have some lists and I have a target. Have you written a binary search algorithm? The easiest way to, or I can't remember, do we have a binary search algorithm defined earlier in this? Oh, here we go. Find. All right, here's our binary search algorithm. So yeah, here's his binary search algorithm. So while I don't have to, I'm going to perhaps rewrite this name. Right, we have a binary search procedure, so we need a sorted list. So 23, 34, 36, 40, 47, and 52 is the element 12 in this list. I find elements, sorry. Right, the thing to keep in mind, so let me write a little docstring here. L is a sorted list. Right, this method right here will return a true or false. It will return true if this element is found. It will return false if this element right here is not found. So that implement insertion on a list using the same principles as binary search. So what we want to do, right, instead of a binary search, I want to insert an element in a list. it said using the same principles as binary search. So we're going to want to assume that the input that we have is a list which is sorted, and an element that I want to insert into this list. And the idea of the binary search idea is, well, we could figure out where do we want to insert this element in this list using a binary search type of procedure. Now, what I might first consider doing is, I'm interested in terms of inserting an element, I'm interested in the index in the list. Right, I need to figure out, like, if I wanted to insert, so let's think about something, I want to insert the value 42 into this list. Right, I want to have a method which will take a sorted list and will insert an element into this list. And I want to find where would I insert this list. Where would I insert this element in this list? Right, I'd want to basically say, well, I want to insert 42 in between 40 and 47. And I want to find that location in using this kind of binary search type of procedure. Right, instead of starting from the beginning or starting from the end and figuring out where I want to insert this, I want to use a binary search procedure to figure out where I would insert this number 42. So I want to write some code. Let's write a insert method, which will take a list and let's say a new element that I want to insert. So L is a sorted list. Let's use numbers right here. New element is a number that I want to insert into L. I'm going to assume that the new element may already be in the list, but I still want to insert it. Note, new L may already be in the list. If so, we still want to insert it. This is just some decision I decided I'm going to make, right? I might allow duplicates. That's fine. What we want to do is we want to find an index where, the kind of breaking point where I want to say, well, everything, say, at or before this index is smaller than this number. Everything, after this index, say, is larger than this number, right? I want to say, well, I have an index 0, 1, 2, 3, and say I want to insert this at index 4. Or what I do is I take this first part of this list, right, slice the list, add a new list with one element, and then slice the rest of the list to create the new list. Right, so I want to find this new, this kind of breaking point. What is this index? using a binary search kind of procedure. So there's a few cases to check, right? So L right here is sorted. If my new element is less than or equal to, first of all, if the length of L is 0, this is a very special case, but I'm going to include it for completeness. If I give you an empty list and I want you to insert a new element, well, I return a list with that new element in it. Right? So if my list is empty, generate a new list with one element. Because I'm including this check because, well, my next check, if I give an empty list, it would fail. If my new element is less than or equal to this L0, right? My new element that I want to insert is smaller. I'm going to return, I'm going to take my new element as a single list and add my list here, right? I'm going to basically append my given list onto the end of a list with one element in it. Similarly, if my new element is greater than or equal to the last element, what am I going to do? I'm going to take my list L and append a list with this new element added to the end. Right, these are all, special cases. Right, so an empty list, I return a new list with one element. If my new element is smaller than the smallest element, I will stick it at the beginning. If my new element is larger than the last element, I will stick this element at the end. Otherwise, now I need to do this binary search type of procedure. So I'm going to do something similar. I'm going to compute like the midpoint in terms of an index. My midpoint is the length of L divided by 2, integer division. And then I'm going to check. I'm going to check the value of my list at this midpoint. I might want to rethink my conclusion that this element is, already in the list. It might make things more complicated. Right, but I want to do something similar. I want to check what is the value of the element at the midpoint of this list? Do I want to, have I found a location here where I could insert this new element, or do I, kind of need to search on the left-hand portion of the list or the right-hand portion of the list? Now, we're out of time here today, so we're going to have to pick this up tomorrow. right? But again, the idea is the same. You know, I've taken care of some special cases. Now, I'm not in these special cases. I need to consider, you know, this point in the list, and I want to check, well, have I found a location where I might insert this new element? Right? I'll compare my element to the value at this midpoint, and, you know, say like beyond, you know, and right, do I, you know, have I found the location where I can insert this element? If not, is this element, you know, do I need to look at the left-hand portion or the right-hand portion of this list to continue? Tomorrow in the later session in the day, it will be 4. It'll be 4 p.m. For me. Right, we're always in Unit 1 in the Unit 1 sessions. So, you know, check your Jupyter pod for when the office hour is for you. Tomorrow it is at 4 p.m. for me. That's my time. Right, so we need to write some more code right here. But again, we want to use this kind of binary search-like procedure. So, yep, we'll come back to this right here, and, you know, we'll finish this up tomorrow. So think about what kind of code that we might need to write here. So I will see you tomorrow. Thanks for the questions. Thanks for your attention.